We left off with ready to do number 34. Okay. So which of the following has a bond order of 1.5? We're looking for bond order out of these possibilities. Let's see, we've got O2 plus John, and 2, O2 minus, and C2, and no, of course. All right, so if we find one, then E's out. So if we're looking at use the shorthand method for the 1s combination of 1s orbitals into the sigma 1s, we'll just leave that out because it won't have an impact on the bond order. And we'll start off with the 2s, and then we have a sigma star 2s, and then we go to the p's, and oxygen and fluorine have no mixing. So you're going to start off with the sigma from a 2p, and then you're going to have a pi from a 2p. And actually, the order doesn't matter when we're doing bond order. It only matters for other things like paramagnetism and diamagnetism. But for determining the bond order, it doesn't matter if these are the right order or not. Let's see. And then we have pi star 2p and sigma star 2p. That might be enough. Let's see. How many valence electrons do we have for these two oxygens? That would be 12, wouldn't it? 12 electrons. So we have 2 here, 2 here, 2 here, and 6. 4 here would be 10. We have 2 more. There we go. Okay, so the bond order calculation for this one, actually, we're not finished because we lost one of them. So I need to take this one and go back down to 1, and this actually should be 11. Okay, now we can do the bond order. So we have 4, 5, 6, 7, 8 minus 2, 3 divided by 2. So that's 5 divided by 2 is 2.5, isn't it? Okay. Nitrogen. Nitrogen's going to flip these two right here. So just to be kosher, we'll do that. So this is going to be star. This one's going to be yes. This is going to be star B. So this is a complete neutral molecule with 10 electrons. We have 2 here, 4 there, 2 there, and that would be 10. 10. That would be 10 right there. Right? So for 8 minus 2 over 2, which is 3. Okay. This one we just take. I'm just going to go out here and say this one star 2p. Everything else is the same for this oxygen, except instead of 2 here, we would have 3. So this would be 13 electrons. Because we had 12 with the neutral, we added 1 more. Okay, so in this case, we've added 2 non-bonding. So it should be 8 minus 5 over 2, right? That's 1.5. So we found the one we want right there. If we did carbon, just for fun. Let's see. Carbon would be 2, 4. And it would be like this array. Yeah, like this arrangement. All right, so it'd be 4 electrons. Oh. Okay. That would be it, wouldn't it? 1, 2, 3, 4. Oh, 8. Duh. 2 of them. There we go. So that would be for 6 minus 2 over 2. So that would be 2. Okay. Got our answers. Moving on. I think it's easier to use these guys because they just smear it. Whereas the microfibers try to remove it all, and that makes it harder. Although it leaves a cleaner surface. Personal preference. Okay, let me see. I'm going to move these where I can. Might have to read the board instead. 36. Which of the following statements about the molecule Bn is false? Assuming sp mixing. Okay, so for this molecule, if we have Bn mixing, they're both in the second period. So we're working from no mixing, right? Oh, assume mixing. Okay, so we're going to have sigma, oops, wrong place. Sigma star, 2s, 2s. Then we're going to have sigma 2p, and mixing is going to put, oops, mixing is going to put the pi first, isn't it? Yeah. There we go. And then we're going to have pi star and sigma star, maybe, if we need them. Okay, so we have boron has 3 electrons, nitrogen has 5, so we have 8 electrons total. 2, 4, and 4 is 8, right? That it? I did that right. Okay, now what's the question? Oh, which is okay. So we have paramagnetism, bond order, total number of electrons. Right, that can't be it. We already figured that was 8. 2 pi bonds. Okay, what we need to do is calculate the bond order. So that's 6 minus 2 is 2. So the bond order is 2. Right? I did that right. Paramagnetic. Wait a minute. Oh, which is false? Could have had a V8. All right. So A is false. This is diamagnetic. Right? It has no unpaired electrons. Right? So A is false. Total number of electrons. We only used 8 of them. But there's a sigma 1s and a sigma star 1s with 4 electrons. 2, 2, and 2. Right, so a total of 12 electrons is true. It has a total. We typically only use the valence electrons because it's easier to do. But with a question like that, we have to be careful. There are actually 12 electrons. 2 pi bonds. Has 2 pi bonds. 2 pi bonds. I don't think so. It has a sigma, bond order 2. It has a sigma and a pi. So D is false also. Ooh, hadn't noticed that one. I think I remember seeing a note in here, a reminder that, hold on a second. I just didn't make the correction there. Issue. But the way the question is written, it could be A or it could be D. So E probably should be 2 of the above. Yeah, because you only got 1 pi bond. You can't have 2 pi bonds and no sigmas. Let's do this. That'll leave a cleaner surface. All right, 38. Which of the following molecules or ions is not paramagnetic in its ground state? All right. I should have left some of those up there already. B, C, D, and E. So we're looking for not paramagnetic. Not paramagnetic. All right, O2. O2 plus. B2. NO. And we assume no sp mixing. Okay, so we're taking the side of oxygen rather than nitrogen. Dioxygen would be no mixing, dinitrogen would be mixing. So we're saying that no mixing. Okay. So let's go back and do 12 electrons. Let's do that first. 11 electrons. 2 borons is 6 electrons. These are valence. NO would be 5 and 6 is 11. And fluorine's 14. There we go. Okay, now we can put it together. O2 is going to be no mixing. So we're going to have sigma 2s on a star, and then a sigma pi 2p 2p, and then a pi star 2p sigma star 2p. This one's going to have the same setup. Boron is going to have mixing. All right, so boron's going to have 2s. It's going to have a sigma. No, it's going to have a pi start. Pi first. That'll be enough. And then NO is no mixing. So it's going to be like oxygen. I guess better write that one out. It means 11. Room for 11. You may not need all of them. Okay, and then fluorine is no mixing. Okay, so let's fill it in. 12 electrons. 2, 4, 6, 4 is 10, 2 more there. I'm gonna leave that up there. No, we don't need it. We just need to reduce this one by 1. Like that. And the rest of them are the same. This one has 6 electrons, 2, 4, 6, 11, 2, 4, 6, and then 4 is 10, and then 1 there. So don't need that one. And then 14. 2, 4, 6, 10, 14. Yep. Yep. Okay, so there we have our, what are they asking us again? Not paramagnetic. Not paramagnetic means diamagnetic. If they have paired electrons, all of them are paired, then it's not paramagnetic. Paramagnetic would be unpaired electrons. So let's see, paired, 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 and paired. So this is diamagnetic. And paired, 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 paired. Oops. What am I thinking? That's paramagnetic. Nobody called me on it either. Shame. This has only got 1. So it's also paramagnetic. You just need an unpaired electron to be paramagnetic. This one's paramagnetic also. Because it has 2 and only 1 each, like that. This one's paramagnetic. Right, so I got 1 here. And this one is diamagnetic. That's the E. Not paramagnetic. Right. It's 38. Let's check out 39. In the molecular orbital description of carbon monoxide, assume sp mixing. We'll look down here and see if we're going to need these anymore. Oh, that's not marked. Okay. All right. Back to 39, right? 39. Okay. Molecular orbital description of carbon monoxide. Assume sp mixing. Okay. Highest energy electrons occupy antibonding. 6 molecular orbitals contain electrons. There are 2 unpaired electrons. The bond order. Okay, so we do need to draw the molecular orbital structure of this one. So if it's got sp mixing, and we're only looking at valence electrons, carbon has 4, oxygen has 6, so that's 10 valence electrons. Now, are there any that require period 1? 6 molecular orbitals contain them. Yeah, we probably better do all of them, just in case. So this is going to be 6 and 8 is 14. 14 electrons total. So now we have to start at, oops, see, sigma formed from 1s, sigma star from 1s, then sigma from 2s, and sigma star from 2s, and then sigma sp mixing, and pi from 2p, sigma from 2p, pi star from 2p, and sigma star from 2p. Should be enough. Okay, so we got 14 electrons. 2, 4, 6, 8. And 4 is 12, and then 2 more. So we don't need these. Okay, now we can answer the questions. Highest energy electrons occupy anti-bonding orbitals. No, A is false. B, 6 molecular orbitals contain electrons. Well, that's true. Okay, 6 molecular, that's true. C, there are 2 unpaired electrons. Nope. They're all paired. Right? These only have 1 each, so there's 2, 4, 6. That's paired, that's paired. This one has 2, and it's got 4. So they're all paired. Now D, the bond order is 3. All right. Bond order is 2, 4, 8, 9, 10 minus 2, 4 divided by 2. That's 6 divided by 2 is 3. That's true. All the above are false. Well, we got 2 true ones. 6 molecular orbitals contain electrons. Okay, that's another boo-boo. D is true. And B is also true, is it not? Unless I made it miscalculation. Carbon has 6 electrons. Oxygen has 8, that's 14. Then we have the 1s sigma sigma star, the 2s sigma sigma star, the pi from 2p, and the sigma from 2p. And then we have 2, 4, 6, 8, 10, 14. Yeah, both B and D are true. All right, so there's another clue. All right, carry on. You bring things up to date. All right, 41. Which of the following statements about CO3 2- ion is, which of the following statements is false? That's true. The way it's written, there can only be one that's false. Assuming I didn't make another mistake. All right. The orbital on the carbon atom are sp2 hybridized. All right, so we've got a combination here. If we were to draw this with the VSEPR model and then look at it, this is going to be a difficult one to draw for the molecular orbital model. I'm not sure how we're going to do that. Let's do A first. sp2 hybridized. Is it sp2 hybridized? All right, so we got valence electrons, 4 here, and 3 times 6 is 18 plus 2. All right, so we have 24. 24 electrons. Carbon. 3 oxygens. And 2, 4, 6. is 18. 2, 4, 6, 10, 12, 14, 16, 18. That's it. Okay. 2 minus. Okay, so sp2 hybridized on the carbon. Yeah, that's true. A is true. sp2 hybrid carbon. All right. How about B? Expected to be diamagnetic. All right. I'm not sure how we're going to answer that one. Because if we look at it from this standpoint, all the electrons are cleared, so we would expect it to be diamagnetic. We have no unpaired electrons in there. But if we drew the molecular orbital for this, I'm going to try and use only the valence electrons. So we have 1, 2, well, there it is, 24. Right. So if we do it like this, starting with 2s, and carbon and oxygen. Did we say carbon oxygen in a previous problem was sp mixing? Okay, so let's go with that. Let's say we have sp mixing. Then we have, let's see, 2s, and then we have pi and from the 2p, sigma from the 2p, then we have pi star 2p, sigma star 2p. So this would only give us what? 2, 4, 8. That would only give us 2, 4, 6, 8, and 8 is 16. That only works out to 16. All right, so I don't know what I'm doing. If we're working from the VSEPR model, we expect it to be diamagnetic. That's the only way I can rationalize the answer for this one. It may not be diamagnetic, but since we don't have the molecular orbital sequence, then we can't fill in the electrons. So we have to also, well, you can't say because it's even numbered, because if it's even numbered, you could still have unpaireds in the pi orbitals. Right, so we just have to assume that based upon VSEPR, then we're going to have expected to be diamagnetic. The CO bonds are different lengths. False. Those bonds are all exactly the same length. Okay, we found it. At least the one that the authors prefer. Has total of 24 electrons. Well, but that's misleading too, because it has a total of 24 valence electrons. Right? But if we say total electrons, we have 3 times 8 is 24, and 6 is 20 is 30. Right? So D would be false also. That question's kind of messed up, isn't it? We're saying that it should be 24 valence electrons. If that's the case, then yeah, it's true. Well, I'm finding a bunch of bad ones in this. I don't know, how did I treat it in the worked problems? 40. Yeah, the problem is the answer is what we expect, but the problem is worded incorrectly. It's not 24 total electrons. It's 20. Oh, I'm sorry. You're right. 41. It should be 24 valence electrons. Okay, if any of these bad questions sneak their way into the exam, be sure and call my attention to it. All right, now we'll go to 42. How many electrons are involved in pi bonding in benzene? How many electrons are involved in pi bonding? Oh, that's benzene. Benzene can be written like this, like that, like that. That means 2, 4, 6. 6 electrons are involved in pi bonding. Okay, that was very simple. Five. All right, which of the following has the highest bond dissociation energy? That means which one has the strongest bond? If we look at bond order, that'll tell us. Because the higher the bond order, the more energy it takes to break it. So if we look at, I think we can, if we just draw N2 again, I think we can answer our questions. Sigma 2s, sigma star 2s, 2, mixing. Pi 2p, sigma 2p, pi star 2p, and sigma. I don't think we need that, but do we? So this is 10 electrons, 10 valence electrons. 2, 4, and 8, and then 2 more. All right, so we don't need these others. Oh, we might. Hold on a second. Because we're going to make some ions too, aren't we? So we'll leave those there. All right, so the bond order here, we know it's 3. We've calculated this one before. If we go to the ions, N2 minus, N2 minus, N2 2 minus, N2 plus, and N2 2 plus. All we really need to do is say, if we add an electron, where's it going? It's going into an anti-bonding orbital, which would reduce the bond order by a half. Okay, because it's divided by 2. It's only 1 electron divided by 2. We put 2 electrons out there, that reduces the bond order by a whole. Then if we add 1, oh, excuse me, I'm backwards. Hold on a second. Oh, that was right. Add an electron, add 2 electrons. 2.5, 2. Now we're going to take away electrons. You take away an electron from a bonding, and that does the same thing. Only it affects the, let's see, 8 minus 2 over 2 is 3. We were affecting this one by adding negatives. Now we're affecting this one by removing the positives. So we're doing effectively the same thing. And this one still has the strongest bond. It has the triple bond. And this is a 2.5 bond. That's a double bond. So that's why the bond dissociation energy is highest for neutral dinitrogen molecule. 47. All right, which of the following molecules or ions does not contain a central atom with D2sp3? C, E. And E says all contain D2sp3. D2sp3. So that means what? Octahedral 3, 4, 5, 6. 6 groups. F5 plus IF minus SF6 and SE5. Is that a minus? I think it's a minus. Okay. So let's do valence electrons first. That's 5 times 7 is 35. So 35 plus 8 minus 1 for the positive charge. So that's 42, right? This will be 4 times 7 is 28, 29. Well, let's see. 5 times 7 is 35, 36. 36 electrons. Sulfur is 6 plus 42 is 48 electrons. And selenium is also 6. Well, this time it's 35. It's 41 plus 1 is 42. Okay, now we can draw our structures. So if we have xenon and, let's see, 5 fluorines. 2, 4, 6, 8, 10. So that's 32 left over. 2, 4, 6. 6 times 5 is 30, right? And now we have 2 electrons. That's 6 groups. This is D2sp3. Then if we have iodine in the middle and only 4 fluorines around it, 2, 4, 6, 8. That would be 28 left over. 2, 4, 6. Right? 4 times 6 is 24. So 24 would be 4 electrons. 2, 4. That's D2sp2, 3 also. Right? 6 groups. 1, 2, 3, 4, 5, 6. SF6. Better than that. Try that again. There we go. With fluorines. 2, 4, 6, 8, 10, 12. So that's 36, right? 2, 4, 6. 6 times 6 is 36. This one is also D2sp3. Then selenium and 5 fluorines. 2, 4, 6, 8, 10. That'd be 32 left over. 2, 4, 6. 6 times 5 is 30, right? That leaves us 2 electrons. Well, they're all D2sp3. Right? So the answer is E, right? Yeah. Okay. Any fill in the blanks. Those are notes. You could probably do those in your sleep. We've done paramagnetics and dimagnetics before, so I'm not going to stop on this one. It's not highlighted anyway. Bond order for each of these. Consider the structure of glycine. Okay. That might be worth looking at. Let's see if there are any other highlighted. Yeah, there's a highlighted one. Okay, so we'll go ahead and do this one. All right, number 60. We need a table to this one. All right, the only thing that we're given in this one is molecule A has sp3 hybridization. So we need electronic geometry. We need hybridization. Oops. Hybridization, bond angles, and examples. Okay. Then we have molecule A, B, and C. All right, the one that we're given is hybridization. This one's sp3, and the other characteristics are given in the problem itself. Let's see if I got a different color. About purple. It works. Okay, consider three molecules. A has a hybridization of sp3. B has two more effective pairs. If it has two more effective pairs, what are they going to be? sp3 is used all up. We need D2 sp3, right? Molecule C consists of 1 sigma and 2 pi's. What that tells me is you have to have a sigma before you can have a pi. So if it's only got 1 sigma, those other 2 pi's have to be between the same 2 atoms. So this is a triple bond. And that means it has to be sp hybridized. There can only be 2 groups around any one of the atoms. So that one has to be sp hybridized, and this molecule is also going to be linear. This one's going to be octahedral. Electronic geometry. And sp3 is tetrahedral. Okay, we got that much done. Bond angles. For tetrahedral, nominal bond angle is 109.5 degrees. sp is obviously 180. Now, the bond angles for the octahedral depends on whether all those positions are occupied by atoms. If they're not, then you don't have a bond angle. But the possibilities for an octahedral, like you have something in the middle, like that. So you can have 90 degrees here between this one and this one is 90 degrees, and then the others are 90. You can also have this one versus that one is 180. So the possibilities are 90 and 180. Yeah. Those are the possibilities. Examples. Methane is a good one. Carbon tetrachloride is a good one for tetrahedral. You can also have, if you want tetrahedral electronic geometry, you can also have ammonia, right? Because it's electronic tetrahedral. Octahedral, SF6 is good. It would have both of those possibilities. And then we had some other octahedrals. I mean, we drew 4 other ones on the board just a minute ago. Linear, dinitrogen, triple bond, carbon monoxide, triple bond. Okay. There. Those are good examples. Inside is not here. See it. Nope, it's not there. All right. All right, 61. Let's see. That's kind of big. Let me shrink it a little bit so we can see more of it. So we have these two electronic structures. One on the left is dinitrogen, and one on the right is dioxygen. And their molecular orbital setup is given there. And from that, we want to infer, well, actually, that's the answer, because this is a key. So the problem says, draw molecular orbitals for dioxygen and dinitrogen, right? And that should be fairly simple because you're going to have the useful information for those. You just have to be sure you're using the right one and label it correctly. Explain why the removal of one electron in O2 strengthens the bond and the removal of one electron in dinitrogen weakens the bonding. We've done that before, but you need to put it in words. If you remove an electron from dioxygen, you're removing it from an anti-bonding orbital. So that increases, by removing the negative from bond order, that increases the value. And for nitrogen, if you remove one, you're removing it from a bonding order, and that decreases the bond order by reducing the positive side. Okay. And calculating the value might help also. Explain your point. Oh, that's it. All right. Do we have any? Did I skip any that anybody wants to look at? I usually ask before we start, but I didn't this time. Are there any ones in there that gave you trouble that you want to talk about? Or did we cover most? I think we covered most of the topics between last Thursday and today. Otherwise, it's all over till Thursday.